Hi everyone. Uh, we're back for the second part of the first lecture. Anyway, tomorrow I will send you an email with a link to join me on Zoom. You can log on it from your Isidore, and we're gonna have not problem session. It's like an office hours. You can ask me questions. I will be there if you log on. I cannot force you to log on. I'm not gonna take attendance. You're adult, so you're on your own. I will be there for you if you need me. So tomorrow, for 169 section 2, I will be on at 12:30. And for section 169 section 3, I will get on at 2 o'clock. Okay? That way you should have those slots are reserved for this course anyway. Thank you. And the same thing for the exam next Tuesday. Section 2 exam will be available to you at 12:30 on Isidore, and section 3, the exam will be available to you on Isidore at 2 o'clock. Okay, I will give you more instruction later on. All right. You know, it takes a real man to admit mistake. We made a mistake here in the first video, so we're gonna come and correct it. Okay, I made a mistake that a pre-calc student will not do. You see this one here, this one, this is not true. It's supposed to be 1 over n. So I made a mistake. So therefore, we're gonna erase the whole thing, at least this part. Okay? So this part we're gonna erase. Because I knew when I constructed this example that this series diverge. All right, so this will be the lim as n goes to infinity, ln of 1 plus 1 over n over 1 over n. And that is, if you take the limit, that will be 0 over 0. And then we're gonna use L'Hopital's rule. Okay? We use L'Hopital's rule. So this is the lim as n goes to infinity, the derivative of the numerator divided by the derivative of the denominator. Remember, I am not teaching you the kosher rule the wrong way here. It's the derivative of the top divided by the derivative of the bottom. Okay, so the derivative of ln will be, this derivative will be minus 1 over n squared over 1 plus 1 over n over minus 1 over n squared. And so this is the lim as n goes to infinity of 1 over 1 plus 1 over n, and that is 1. So thus the lim as n goes to infinity of 1 plus 1 over n is the lim as n goes to infinity of e to the y, and that is e to the 1, and that is e bigger than 1. Bigger than 1, then the test tell us, remember if the limit is bigger than 1, then this one diverges. All right, so let's go back to it. So I guess you may say Dr. Raful is a nerd. He has a whiteboard in his house. I guess I am. So the series diverges. This is not really 100% correct. What I meant to say is the series diverges. Okay? So there we go. All right. So now I am going to propose, I'm going to throw at you a few problems, and then you're going to decide what test to use. Because in real life, no one is going to tell you which test to use. Okay? All right. Okay, so let's look at, I constructed some problems for you. So let's take a look at 1 n equal 1 to infinity n minus 1 over 2n plus 1 to three Okay, so let's start with those, and I got more. Maybe we'll do here 4 2 to the n over n factorial 5 1 over 2 plus 3 to the n. So the question will be decide whether the series converge, diverge, conditionally converge, or absolutely converge. Is that clear? So now it's up to you which test to use. Some of them you may have more than one test that is available. But remember, when you can easily take the limit, the divergence test comes really, really handy. Is that right? The divergence test comes very, very handy. So let's take a look at this problem here. So if you take, this is an, if you look at this as an, and we know this is 1/2, and that is different from 0. So what does the divergence test say? So by the divergence test, the series diverges. Okay? So the series diverges. There we go. Remember, this is n cubed. Okay? All right, so this one, really hard. It's a tough one. You don't want to use the ratio test on this one. Can you imagine trying to calculate an plus 1 over an for this ugly expression? Every time you see polynomial, try to use a comparison test or the limit comparison test. Okay? So for this one, let's try limit comparison test. So we're going to take Bn equal, remember at infinity, the dominant term on the top is n cubed, and the dominant term on the bottom is 3n cubed. How's that? Okay? And then this is n to the 3/2 minus 3 over 3. So Bn is n to the 3 minus 6 minus 3 over 2 over 3. So this is 1 over 3 n to the 3.5. Okay? And so now we're going to take the limit as n goes to infinity of an over bn. So that's what you do when you look at the limit comparison test. So I'm going to erase this part here. You see, this one was really easy. And if you do the divergence test here on this one, you see the power of this is smaller than this. So the limit will goes to 0, and that doesn't say anything considering if you are trying to do the divergence test. Okay? So, okay. Now, I don't want you to be confused. Now, I looked at the video, and I can see the cross above the door. So don't be confused. I'm not at UD. I'm at my house. I'm in the foyer. All right? Yes, when we moved into this house about 2006, we built this house, we moved in it in 2006. The priest, the Catholic priest, came over, blessed the house, and he gave us this cross, and we put it on top of the door. All right, so now we have the story. Okay, so now my wife and everybody else see how I joke around with you guys, and I tell you stories. Okay, I'm getting tired though of this being at home all the time. My kids won't let me get out because they think I'm almost 60 years old and I should not be outside the house. Ugh. All right, so let's take a look at the limb as n goes to infinity of an over bn. Okay, so this is the limb as n goes to infinity over 3n cubed plus 4n squared plus 2 times 3n to the 3.5. Okay? So we're gonna do the limit. Okay. So, yuck. All right. So this is the limb as n goes to infinity. Remember, at infinity, the top behave like n to power 3.5 times 3n to power 3.5 over 3n cubed, and that is 1. All right. So because this is the limb as n goes to infinity of n cubed over n cubed, and that is 1. So that is positive. So either both theories converge or both theories diverge. So let me hear. So by the limit comparison test, either both converge or both diverge. But of Bn is what? Where is it? It's this one here, is 1 over 3n to the 3.5, and that converges by the integral test, since a p is 3.5 bigger than 1. So we proved that this one converge, therefore this one converge. Okay, diverge, the first one, converge. What do you think the other one here? Okay, I'm gonna keep this on the board for a second, then we're gonna take it out. I mean, erase it, take it out. Listen to this. Okay? All right, so let's erase. We did all the work. Nice work. You helped me do it. Now it's time to move on, and let's try this one. So first of all, this one, let's try to test for absolute convergence. For 3, let's do absolute convergence. So we look at minus 1 to the n cubed over n4 plus 1, and that is n cubed over n4 plus 1. Is that right? And then apply the divergence test. By the divergence test, it diverges, since the limb as n goes to infinity, n cubed over n4 plus 1. Sorry, mistake. Nope, that's what I said is garbage. All right, so we have n cubed over n4 plus 1. Okay? Well, This one, let's do comparison test. Wire comparison test will not help us here because, so what we're gonna use is, how would you test for convergence? That we just figured out divergence test doesn't work. The integral test, you'll have to integrate this one. It's very hard. What about the comparison test? So let's try the comparison, a limit comparison test. Let Bn is n cubed over n4, that is 1 over n. So the lim as n goes to infinity, so n cubed over n4 plus 1 times n, and that is 1 bigger than 0. Again, they either both converge or both diverge, but Bn is 1 over n diverges. So, by the limit comparison test, n cubed over n4 plus 1 diverges. Okay, there we go. How's that? So, does this converge absolutely? No. So, conclusion. Okay. So, it does not converge absolutely. You see that? Okay. Now, let us test for convergence. Okay. Now, the original series is alternating with an is n cubed over n4 plus 1. They're bigger than 0. An are decreasing, and the lim as n goes to infinity of an is 0. So, by the alternating series test, this series converges. Okay, so converges. So what do we call a series that converge but does not absolutely converge? What do we call it? Conditional convergence. So this one converges conditionally. So when do we test for conditional convergence? We test for conditional convergence when we have an alternating series. Because if the series doesn't have negative terms, if you take the absolute value, you're going to get the same series back. So there's no need to test for absolute convergence. Okay? So you only test for absolute convergence when you have an alternating series. So that is answer. This one I will do next time for you. And this one I will do next time for you. So you do this on your own. Next lecture, I will go over them and we'll pick up the other things from here. But you need to remind me, Professor Raful, you need to finish this one and this one. So I'm assigning them as homework. Okay? So here there is no absolute convergence. It's only convergence. I believe for this one you will leave the ratio test. Okay? And for this one, it's very, 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 very easy. Try the divergence test. Okay, so now let me give you homework. So I'm going to keep them on the board. So the homework, page 617, number 23 to 45 odds. Okay? And there are a lot of things we can do. Try 57. And you think that's enough for you? Okay. All right. So this is your homework. I will be waiting for you on Zoom. I will send you an email with a link to log in. And have a great night. Thank you very much.